Hello everyone, it's September 25th. Alright, we had an easy one last night, so today I'm prepared. Let's see what we have. Shortest path in a grid with obstacles elimination. You're given a n by n matrix where each cell is either 0 or 1. 0 is empty, 1 is obstacle. You can move up, down, left or right, from and to an empty cell in one step. So up, down, left or right. Return the minimum number of steps to walk from the upper left corner to the lower right corner, given that you can eliminate at most k obstacles. If it is not possible, return -1. Alright, smaller than 40, so I'm looking at something very costly in time. And the start and end will both be okay. Okay. k equals 1, it'll be 6 steps. So we said that we're 1, 2, 3, 4, 5, 6. Alright? Without elimination, it's 10. We should have with one obstacle elimination. At position 3, 2. 3, 2 is this one. It's 6. 1. It can do it. These two obstacles to find such a walk. Okay, so a walk is just going to be a traversal, right? Let's say a traversal and go to the right and go down. Go left. No, we just record the steps that we've taken. I'll record the step that we've taken. I mean, if we say like dynamic programming, which it should be, right? What we have is we can compute, right, at each position how many steps that we need, right? At this position, we can go up, right, or we can go down. I think I have this type of problem in the past, and I always got confused. How do we walk a grid where we have like all possible 4 directions to go, right? 4 directions to go. Four directions to go. If we start from the end, right, and we say these has 1 step, this is 0 step. About this one, well, we can go up, we can go this, we can go this and this. So yeah, how do we do in the past? How this type of problem? I think we usually do it like, is that like 2 ways? Like we go right and then go down, right? And then we go left and then go up, right? I don't remember. This is my weakness. I never know how this one is supposed to be done. I don't remember. Because at any position we have 4 directions to go, right? And we can say the places you've gone already, we don't go. Okay. But how about the places that we have not gone to? Well, at each position, you can go up, you can go left, you can go down, you can go right. So we have to go 4 different ways. and we will record, right? This one will go right, and also will be how many steps this one needs plus 1, and how many steps this one needs plus 1. And from this, I don't go back. I can go down, I can go here, and then if this one's already visited, so I call it already. So I think with this, if we cache it well, it should be OMN to compute the total number of steps. I mean, we say at most K obstacles. Can be removed. So are we saying we're gonna have I, J, and K? I probably shouldn't call it K. Let's call it IJT, right? T is the number of that has been removed already. So if T equals 0, right, that's what we have already. So we can do that. How about T is 1? Like at any position, right? At any position, and we say we have 1 removed. But which one? So as we go, right, as we traverse for any node, as we traverse, we will hit a node. We'll hit an obstacle. So whenever we hit an obstacle, and we say we have two choices, right? We either remove it or we leave it. So let's just say we have two choices. Let's say we remove it, right? Okay, we remove it so we can go that way, but we need to record that we have removed one. And or we don't remove it. That's two different ways. We don't remove it, then we go the other way. Okay, and then what does this mean? This just means this position. When I go down, so this position, the remaining T. No, we can't cache it though. How can we cache? I feel like you need to think about it differently. Now the shortest distance, right, is going to be m plus n. 1, 2, 3, 4, 5, 6. It's actually no, it's m plus n minus 2, right? Yeah, it's m plus n minus 2. That's the shortest distance. It cannot be shorter than that. That's the shortest. So what are we trying to say? I mean, what we can do is analyze it and see like what are all the possible. Hold on. Shortest path. Oh, this is tough. This one's tough. I remove this, right? I'll go to remove this, so this one gets removed. Now we cannot just remove. It's not gonna work. Let me think. So what we're saying is, what if we find shortest path and then count in all these shortest paths how many obstacles there are? Okay, what are you saying? I'm saying if we go and any path, right? Any path, we generate all the paths that we can. And as we go to, every time we go to, and then we don't go to the place that we've been before. So we only explore new places, right? New places. And at each position, I'll have the shortest distance, right? Let's say, but that's the shortest distance. At each position, I have a shortest distance, right? So like at this position, and I need to go, I can go here, and I can go here, 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 and then I obtain, and then I can go here, 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 here. I can go all like this. I'm thinking about ignoring the ones. Right? If we ignore the ones and try to create a path, and we will arrive at the shortest distance, right? The shortest distance from any position to the end. That will be 2, but require removing 2. That will be 2 require removing 1, right? So we can build it up. Okay, let's say we have that as the shortest distance, ignoring ones, but we count how many obstacles we're facing, right? And then if the total number is smaller or equal to k, then we know, right? But what if the total number is not smaller or equal to k? If it's not smaller or equal to k, like here, that will be 2. That will be 2. No, this one's tough. Let me draw it up. So we have 1, 2, 3, 4, and 1, 2, 3. And 1, 2. 0, 0, 0. 1, 0, 0, 0, 0, 0, 1, 1. 0, 0, 0. So we go here, look at the first level, and then it's the second level, third level, right? Fourth level, fifth level, sixth level, right? So as we go, we hit obstacle, and then we can choose to continue, or we choose not. So 2 ways, right? And then, like if the obstacle, the number of removal is larger, then we don't, like if we're here and we already have used the 1, then we don't use it anymore. So we go here, no, so we go down, right? And then to this place, but we can get it from here, right? We can get it from here. We can go, and then all these are all visited, right? All visited. All four directions. Yeah, try all four directions. If I did it before, we don't do it again. So at each position, right, at each position we will have now that's not stable. The value can change depending on the future. Because if I'm at a cell, right, and then the steps is not determined by me, it's determined by the future. The future is not stable. Because in the future, I might ignore an obstacle or I might not. So it's hard to say. But even if the goal, let's like the goal is the 1k obstacles. Wow, I have no idea. I'm royally stuck. I mean, I was thinking like when you meet a stuck when you encounter an obstacle, you have like two choices. You either take it, right, or you don't. But aren't we also supposed to Are we also supposed to like handle all of the situations? Like, what if we don't have, right? Have two. But like there might be one that can allow us like going this way, and this way, right? So what if we have, let's say, this is also a 1, right? Yeah, if this is a 1, and we can remove 1, 1, so we can actually, oh, I can go here. Let's say, so this is a 1, and, oh, I can't. How about we go like smaller problem? It feels like, let's say we're here, right? We're here, and we can do it. And we're here, we can do it, right? The minimum steps will be, we won't be here, so we just go here, right? And then it's like a given matrix. A given matrix at, it's at the top left corner of a given matrix. And I just say, can you reach to the end? Like if we have a smaller matrix that we can do it, how about a bigger one? A small matrix we have, okay, then a bigger one will mean either add a row at the top or add a row at a column at the left side. So if I have a matrix, right, I already know the shortest distance, since why always focus on here? It should be like anywhere, right? Anywhere. So let's say we give it a matrix. I know from anywhere along the outer edge, right, the shortest path towards the lower right corner. I know it. I just know it. So we know the shortest path, and also we know the shortest path. Is that sufficient? We probably should also know. No, I don't see the light at the end of the tunnel. I'm gonna look at a hint. This is hard. Ha! The first hint is called BFS. Okay, use BFS. I mean, BFS will be like going diagonal. That's BFS. And BFS will like 1, 2, 3, 4, 5, 6, right? 1, 1, 2, 3, 4. So BFS will give us the shortest distance. But then what with BFS? I mean, BFS we know first one, we can pick the one that doesn't require, right? Or this one will require one step. And then the next one, so this one, it's like 2 steps. Going here is like 2 steps with 1. Going here, it's like 2 steps with 1. 3 steps with 0. 3 steps with 1. And 3 steps with 1. 4 steps with 0. 4 steps with 2. 4 steps with 1. 5 steps with 1. 5 steps with 1. 6 steps with 1. Okay? Alright. Most K. I don't have a good example, right? Just like if you remove it, yeah, it's like that. What if K is 0 here? Well, if K is 0, we can go all the way to this one, right? No, we can all the way go to this one. And from this one, we can't go anymore. Right? We can't go anymore because from this one, if we want to go to its children, then we hit. This one needs to go like this way. How do we handle that? Or are we saying that each one, and in here we can reach. If I can reach you, then you can reach me, right? Let's say the shortest distance from each position to the end, okay? Which means we can reach here, we have the shortest distance. And from here, so the shortest distance is we can go left. Well, how do we know we should go left? Because the shortest distance requires 1, but we cannot, which means the shortest distance does not work, right? Which means we need to take a route that we can take a shortest route that does not. Okay, so at each position, we know the shortest route to the end and how many obstacles, the minimum number of obstacles we need to traverse. Okay, now with that in mind, so we get at each position, right? With each position we have shortest distance and the minimum number of obstacles we need to go through. Okay, that's fine. We can do that. We can do that. Now once that is done, what do we need? We need to know. Now that is done, for every single one of them, right? So we're gonna go from a start. If I go from a start, and then I look around my neighbors, and then I realize I cannot do the shortest because the number of ones is more than allowed, which means I have to go. Yeah, I have the shortest, okay. So at a certain position, I have the shortest distance with the minimum number of obstacles I need to deal with. Now, if that is too much, right, that is too much, it means I have to not go through some of the obstacles, right? Not go through some of the obstacles. What are the choices? Well, the choices are I can still go, but at each step when I go, I need to consider, like we'll go to the next one, and I have a quota, right? I have a quota, how many ones I can cross. So at a certain point, I look at my neighbors. And my neighbors all have the shortest distance with the number of obstacles. So at my current point, I have like how many obstacles left I can remove. So, and I have the current steps. So from that point of view, I know I cannot go from where I am using the shortest distance because the number of obstacles removed will be too much. So I take another route. So I can look up, look left, look down, look right. And if at that position we have the shortest distance from there, right? If from there the shortest distance is every place is shortest distance, right? So if, like at that position, so I'm at a certain position. I have, let's say, I have t obstacles remaining that I can go, and from my position to the end, I have to go through more than t. So I have to look around to see if there's any path that can get me to the destination with less than t number of obstacles removed, right? If we have less, then I'll take it. I'll take that one, and then we're done. And we have a lot more, and then we just take all of them. Basically, what we're saying is, at a certain point, right? At a certain point, if the smallest distance is too much, like if I go here and then I try to go around, and then I cannot take more obstacles. This one requires, let's say, too much. So if I take that, I will get a higher, right? So like I have to change course. if I'm at a position, I have my neighbors, right? And I'll choose the neighbor whose shortest distance at the moment also allows me, like, also not blow up the quota. If I choose one that already below the quota, right, then I either go that way, but then have to choose some other way, or I go. So it's like every step we try to find, every step we have comparison, we have 4 options to compare. And among the 4 options, we need to choose the option with the shortest distance and the quota in line with what we have, right? Okay, so let's go there. But like if we find that, then the problem is done, right? Like if I at the start and I already know it's going to take 1 to reach the shortest distance, and then this is 1, then we're done. The only problem is at the start, to reach the end, I have 2, right? So from here, I have 2 to go through, right? 2 to go through. How do I know it's 2? I go BFS all the way down. And a number of obstacles. So how do we code that? Even if like I know, okay, it's going to be 2, and I only require 1, then what? That means, and I see like this one requires 2, and this one requires 2 as well. So both my neighbors require 2. That's why I require 2. So I can go to my neighbor and say, okay, so I can require removing 2. So if I go there and say I'll remove it, then from here, optimal will require 1, right? Removing 1. Here, optimal will require removing 1. And I look at my neighbors. Now require, yeah, this basically this is 0, this is 0, right? And look at my neighbors. If my neighbor, so basically I cannot go the optimal from this position, right? I cannot go the optimal. So I need to check my neighbors, and if I see, because I got quota 0, I have a 0 quota, no more quota left. Whereas if the neighbors have a path with 0, then we're good. But if the neighbor does not have a path with 0, then I can choose to go to an empty cell, right? And then from the empty cell, we can keep the same analysis. That means at each position, I have the number of quota left. All right, hold on. At each position, I have the number of quota on the T left, right? Each position, I have the number of quota T left. And then the number of quota yeah, I have the number of quota, right? And I have 0 quota left, so I have to go to a empty cell. And from that empty cell, I have 0 quota, So I have to go to the next empty cell. And then from that, I have to go to the next empty cell. Right? And each empty cell, we're going to see if they have the shortest path to the end with 0. If one of them does, then it's a candidate. If they do not, then we'll try all the options, and then if nothing, then we're done, right? So in this case, my quota is 1, and I currently have 2. Right? I need to remove 2, so that's not going to work. So what's my choices? My choice is I can go to a empty cell, right? While still have the quota as 1, or I can go to a obstacle and have my quota become 0. And now when your quota is 0, the only place you can go to is empty cell, and also the one that you have not visited before, right? Okay, so in that case, I can keep going, right? I can keep going from there to the next empty cell, to the next empty cell, and then I can go up empty cell, whatnot, it doesn't matter, because my quota is 0, right? But if my quota is 1, and go to an empty cell, right? And my quota is still 1, and then from that cell we can check, check. Huh. If I can move from one cell to another cell, I'm not using any quota, so it should be the same, right? Yeah, if the number of obstacles I need to go through to get to the end, let's say from me is 1, then from all my neighbors, oh, but that's not the shortest distance. So I move here, and then we check its shortest distance, and then if it's good, then we have a candidate, right? Now, if we cannot do, right, and we can keep trying, so from this position, we can try to go to the obstacle to remove the quota, or we find maybe this is the way. All right, let me try to run it through. So we're gonna use what? BFS? Yeah, I think we use BFS. It doesn't really matter. Wait, does it matter? Like from each position, I'm only going to go down or go right, right? We go down or go right. Each position go down or go right. And then we need to know the shortest distance. And we know the shortest distance. Right? We know from each position, we know. The shortest distance we already know. So all we want to know is not the shortest distance, but at each position, what is the shortest, what is the minimum number of obstacles I have to go through, right? So if we go reverse-wise, I think this one, the shortest distance is whatever, when we can calculate it. And then it's 0, like t is 0. The number of obstacles to go through is 0. And in this position, I know the shortest distance, and then the shortest distance will be the 1 to down, right? And I have a 1, so this one will have 1. Yeah, let's draw another matrix. 1, 2. All right, so this was 0, and this is 1. I know, and this will be 0, right? And then I think will be like a diagonal one. So I go over here, and then this one will compute like either this will be 0, right? And then this one needs this and this, so we have 0, but so this is a 1. And this one will be 1. Here, I look at these two, and take this one, it's 0. This one, look at these two, both are 1. Right, which means that when you take 1, both are 1, So this has to be 1. And this one here has to be 1. Right? And then here, be 0, has to be 1, 1, 0, 1, and no, this one's 1. My bad. This one's 1. And here's 1, right? So that's the number of obstacles. So we can compute the number of obstacles we have to go through at each cell, at any cell, right? At any cell to reach the destination with the shortest distance. And each shortest distance we can compute based on their I and j. So it can be what? That's m minus I, right? M is what? M is, that's 1, 2, 3, 4, 5 is 5. So 5 minus, let's take 1, 2, 3. Oh, so m minus I will be, I want the length. So n minus I plus 1, right? Plus n minus j plus 1, and then minus 2. So it's going to be m minus I plus n minus j minus 4. Let's see if it's correct. It doesn't feel right to me, man. Right, so what if m is what? M is 5, n is 3. I and j, this one will be 4 and 2, right? So 5 minus 4 is 1. 3 minus 2 is also 1. 1 plus 1 is 2. That's not true. It's the number of rows plus the number of columns. Wait, how do we handle this? Isn't it just, let's say n minus j? This is like how many steps, right? How many steps? So yeah, so no, it's n minus 1. N minus 1 minus j. That's how many steps going right. Plus n minus 1 minus I. So that's going to be m plus n minus I minus j minus 2. And that is the one. Yep, that is the formula to compute the shortest distance, right? So now we have this. I'm going to start from the top left corner, and we're going to count how many ones there are. Only 1, and we can allow 1. Then boom, we solved it, right? One step done. Now, in this case, right? In this case, we can also compute. So we can compute. I'm going to go from lower right. So it's always 0, lower right corner. And in here, it's always going to be 1. And this one, we can go, this one is 0. This one will have a 1, so this one has to be 1. And then this is going to be 0. This is going to be 0. Oh, wait, no, it's a 1. You can see it's a 1. And that is a 1. And then that's actually 2. Now we have a 2. And this position is a 1, so that's also a 2. And this position is a 1, that's also a 2. And this position is 0, so that's a 2. So we have lots of 2's in it, right? Now we're looking at, we have only, the quota is 1, but the smallest distance required 2. So what do? Well, I need to move to my neighbor, right? I need to move to my neighbor. And I have 2 neighbors. And here's the choice, right? Here's the choice. We can move to one neighbor, and it's a 1, but we have to do, so we're going to say, okay, now the quota is 0. Right? Quota is 0, and I'm here, right? I'm here. The quota is 0. Now from this position, right? So from this position, the quota is 0. And I can look around. I can look at my neighbors, so these 2, right? And we say what we can do is if I go here, like my quota is already 0, so I need to go to a place that cannot be an obstacle because I don't have quota anymore, and then no way to go, right? Or I go here, no way to go. So let's conclude it's not possible. But let's say if I can go, right? So I go to a place, right? A place I can go means it's either an empty space, right? We can always move to an empty space, or we move to an obstacle and decreasing my quota. And then from there, we can keep looking, right? Keep looking. And when we say looking, in this sense, we're going to look all 4 directions. And we can only move to a place where our quota allows us, right? If we have quota, then we basically can move anywhere, right? We can move anywhere. And then we move to a place and then reduce our quota. And from that place, until like we move until what? We move until the neighbors, right? Until our neighbor the shortest distance from our neighbor to the end has 1, has the same number as our quota, and that's when I want to let's code it up a little bit. Right? We used the 1 hint, but we actually didn't use it because I'm having a different thought. I mean, I did confirm one thing, right? The hint says use BFS. I'm not going to use BFS. What I'm going to do is compute shortest distance at the number of obstacles that will encounter the minimum number, right? So we're going to compute the minimum number of obstacles that we encounter for each cell if it goes to the end in the shortest distance, right? That's what we want. So what we're gonna say this is num obstacles, num OBS, right? That's gonna be we're gonna say mn equals len grid and len grid 0, right? So this is going to be 0 times n for underscore in range n. All right, so we have number of obstacles for each position. I want to go from the lower right. How can we handle this? These are like diagonal wise. God, diagonal wise. So ij for and when jump, right? When jump. So I j is equal to, let's say start from I is n minus 1, j is n minus 2, right? That's our starting point. So the starting point, and we know this one, so starting point, let's put it here, then we just go this way. Or maybe we can go this, go down, go up, go down, go up, like that. Depends. So while I is larger equal to 0, right? And j is larger equal to 0. I feel like and then we regroup. I will compute a new I, right? And then we regroup. And how do I know that I has to be going up? Is that where the BFS comes in? Like, this is a little bit hard for me to reason, but if the BFS is like from each position, right? That's our children. We always go this way and this way, right? So we go this way and this way. And then, and here, I obtain, so I go 1, right? And then I go this way or this way. And then we always try, if I have 2 options, we go with the one without, right? And then, so I don't go here, this one go here. So here, I don't go here, this one go here. But what about this one? I want every single one to be included. Like this one requires as well. But I mean, the thing is just it's hard to reason. Oh, there's a way. There's a way. Because we can all, let's see. We're filling these 2, right? And if I fill this one, then I can fill, yeah, I can do this one. I can do this way. So I can go this column and this row. This column and this row. So we go like a full column, a full row. So how do we go? So we're gonna say for I, and then for j, right? And then for I, okay, so we have to go from this position, go up, right? And then from this position, go this way, right? And this position can be computed. So we just compute it twice, which is fine. We'll make the logic easier. So what's the end condition? All right, end condition. So our anchor point is here, anchor point is here, anchor point is here. And the anchor point, right, is the anchor point. So we're gonna just say anchor AIAJ, right? Anchor point. We start from m-1 and n-1, right? And we say while AI is larger or equal to 0 and AJ is larger or equal to 0, right? And we say I'm gonna go a full this, right? How do I reason this? I can add another one, right? I can add another one, so this will just be comparing these 2, comparing these 2. Okay, okay. Let's try. So just to make the logic easier, I just add another layer, right? We add another layer, and we still start from n-1, which is, we have another layer, we start from here, right? So what we're gonna do is for, and go up, right? For, you can say I in range from AI, which is this position, to all the way up to 0, so -1, right? And then num this I and AJ, anchor point J, equals to, right, equals to grid I AJ, right? If this one, is it equal to 1, right? Is it not equal to 0 or equal to 1, and then plus the minimum of num this I plus 1 AJ, which is just the lower one, and num OBS I AJ plus 1. So go to the right. So the minimum of these 2, right? Minimum value of these 2, plus if I'm a 0, then this one will evaluate to 0, right? So it will just be okay. So we do that. Now after we do that, we do what? J in range. Same thing. Let's just say from AJ, and then we're gonna go to 0, right? And then same thing. I mean, in this case, we probably we don't have to. We can just say aj minus 1, right? We can say aj minus 1. So aj is here because I already handled, so aj minus 1. So aj minus 1 to the start, and everything is still this and this, right? This and this and this and this, which is fine, So we're going to say the same thing. And this is going to be AI j, so grid AI and j equals 1 plus minimum. This is going to be AI plus 1, so the lower one, j, or AI and j plus 1. Right. So once we've done this, let's say for row in num orbs, print row. Right. I need to check. This is not a trivial question. Okay, how do we import this? Oof. So this is this, and then 1, right? And then handle all this. Okay, so this one will be 0, 1, 1, right? 1, 1, 1, and 1, 0, 0. This one will also return. Oh no, this one will return minus 1. But I don't care. Right? I don't care about the return value so far. What I care about is making sure that this logic works. So I'm going to go this. Oh, I forgot K. Grid and K. Oh, K. I forgot to put in K. 6. That's the answer. So K is here. Oh, shoot. I forgot to update. Hi. So after we're done, AI minus equal 1 and aj minus equal 1. Right? So we go this. Oh, that is not what we want. Give me true and false. We're gonna cast this. There we go. So we don't look at this one. We just look at this part, and that's not right, right? This one's correct. Oh, this one's not correct either. Oh, we have. Holy moly, we have these are zeros, so we always pick the zeros. Jesus. The smaller we'll pick this. Unless if we make all these. Then what about this one? Yeah. Okay. That's the whole reason we're doing this is because I want to make the logic easier. That's the whole reason why we're doing this. In this case, it's not working. So Okay, so in this case, I'm not going to do this one. So let's just go n. This is m. And anchors this, right? And then for AI this, we're just going to check. Right? I'm going to say if aj is equal to n minus 1 and I is equal to n minus 1, num I aj equal to 0, right? Else this is going to equal to what and then plus I and j, right? But this has to be something like this, minimum this or this, right? Then I have to say if I is smaller than m, right? Then we use this. Say if this, if I is smaller than m, I plus 1 smaller than m, else I can say math.inf, right? So we're gonna just get a math. And same thing here. This will be if aj is aj plus 1 is smaller than n, else math.inf. And I already considered this, so we don't have to consider here again. So basically, this will be the same thing. So we're gonna want this, right, and this, and then I'm gonna say if ai plus 1 is smaller than m, else math.inf. Same thing here. If j plus 1 is smaller than n, else math.inf. Now with this, we'll get what we want. That's actually still not. Why is this 2 at this position? Oh, it is 2, because at this position, we're going to go through 2. We're going to go through 2. Ah, that's something I didn't notice earlier. So now this is a 1, right? So let's say this one's good. Okay. So we're gonna traverse this, right? We're gonna traverse this. How do we traverse? Well, say I'm at this position, right? So it's gonna be DFS, right? So def DFS. I need I and j, current location, and quota, remaining quota, how many we can ignore. What else do I need? I need a quota, and I also need steps, steps. And we need a self.res equals math.inf, because we need to record. So and this one will return what will I return? What do I return? I'm in this position, I have my quota, right? And then I have the number of steps that I have accumulated so far, right? And I don't return anything because I'll just pass my steps to the next one, right? Until I reach, like this is number of steps. I have that number of steps, and then I go to the next one and accumulate the steps, right? And the next one is accumulated steps. So this one does not return anything, right? And then we say if I is equal to n minus 1 and j equals to n minus 1, that's it. We are at the end. And we say self.res equals minimum, right? Self.res and the steps. Done. Return, right? Otherwise, then we have a position, right? We're at a position. And we'll make sure that quota is currently allowed, right? It's always larger or equal to 0. Always pass in, okay? So Now what? Now we're at ij, and we have 4 directions to go. Ah, we don't have to go here. That's not the check. The check is to see if my quota, right, is smaller, no, is larger or equal to number of obstacles, ij, right? If my quota is larger than what is needed, then we will return steps, right? The steps is to me plus 1. Let's go to the next one. Go to no, just steps, and plus from this position the optimal, right? The optimal will be, we already computed, m plus n minus I minus j minus 2. All right. Now we return. We do not return. Do we return? Do we return? Good question. Now we don't return, right? We do not return because I said it's return none. What happens if I return? We don't need to return. Let's say self.res equals min self.res, yes, all right, and then return. Here, that's a return. So this is, and we make sure that we do not go beyond the boundary, so we don't have to check I and j here, right? So that's that. Now we're gonna have, say, di, dj in, so the 4 directions, right? In 4 directions, we have what? 0, 1. That is going to right, going down to 1, 0. Going left is 0, minus 1, and going up is minus 1, 0. And we need to make sure we don't go to the spots where we've gone already. So we need a global, let's say visited, right, equals to be a set. We're just going to put tuples in it. It's easier to handle. Okay, so for dij in this, ni and j, next ij equals I plus di and j plus dj, right? And we say if ni is smaller, if 0 smaller equal to ni, smaller equal to m, and 0 smaller equal to nj, smaller equal to n, and ni and j not in visited, right? Now we can visit it. But we're gonna decide whether to visit it, right? Oh, not in visited? Like if I visit it once and it's a no-go, I might be able to visit from a different place, right? Because at each time I visit a node, the quota is different, right? The quota is different. Let's say if I visit a node, right? And I try to visit a node. And if I'm visiting this node with the same quota, so yeah, so I think it's the quota. We have to add, so it's visited including quota as well, right? Quota as well. So it's going to be I, Ni, and Ij, and quota, Ij and Q. So if a cell I visited before with the same number of quota, then I shouldn't visit Again, does that mean you need to return something? Man, you need to return something, right? You need to return it. You need to return. So DFS is given the current I, current J, like in this cell, I have IJ and I have the quota, right? And I want to find out, based on that, what is the minimum steps I can achieve, right? So in that case, I'm just going to return int, and we can always just cache it. All right, and always cache it. Size, max size, none. All right. So we always return, and we always try to find the minimum steps at this quota. Right? Minimum step at a quota. So I say if the quota larger than this, then we return this. Return what? Return the steps that I have from my position down, right? That's what I return. Right? If quota is this, then we immediately return. Now, else, which means the quota is not larger too, and then I need to go through 4 directions. That's fine, 4 directions. And what we're gonna say is blah blah blah, and we don't do this because it has quota involved. If it's within, right? Then I need to say, what is my quota, right? So if this, right, and, right, and quota, oh wait, it's gonna be like this. If this, let's say if grid NINJ is equal to 0, that does not cost me any quota. But do we need to go there? Yes, we do. We do need to go there. So if it's equal to 0, right, and I can have a mini res equals math.inf, right? So if it's 0, then I can go there, right? So I can say DFS NINJ with the same quota as we have already, with the same quota, and this will give me the smallest distance from that position with that much quota. And once we have that information, right? Because that's a 0. Right? If it's a 0, then it's the same quota, right? It's the same quota as me. And if it's a 1, then I need to remove my quota, right? And then I just DFS. So I want to find with that number much quota from that position, right? From that position. And my returns, I'm going to say 1 plus this. So I'm going to say self, not res, equals min, res, and a 1 plus this, right? Else, if it's a 1, right, that means I need to take a quota. So what do? We say elif quota is larger or larger than 0. I have a larger than 0 quota. Then I can say res equals min, res 1 plus DFS, NINJ, quota minus 1. Right? So I have to remove a quota. And if my quota is already 0, then I cannot go. So I just have to keep going. So once I'm done with all 4 directions, I'll have my res. I'm going to say we can return res. We just return res. Res will become maximum. Like if I cannot handle both situations, res will be maximum. So then, what I'm going to do is at this position, I'm just going to call it DFS 0, 0 with k, that's our quota, and this is going to give a result. I'm going to say return this. When does it say res, right? I'll need this. I'm going to say res equals this, and return res if return -1 if res is equal to math.inf, else return res. Okay, these 2 passes. All right, let's see. Let's see. We just submit. I mean, if it fail, we work a little bit, and if we have a runtime error, maximum recursion depth exceeded. Maximum recursion. We already cached. Do we have to cache it ourselves? IJ and a quota, all right? We just say if this one, like, what do you mean? What I mean is, we go in the other directions. That's why. And we're going all 4 directions, so we do go back. And when we go back, this one has not been identified yet, so we just keep calling. So we're back and forth, back and forth. We're doing the same thing over and over again. No, that's not gonna work. But we have to move left, right? We have to move left. Visited? Like, it's the one that we have visited before. Like, this is the position, right? We visited this one before, and then we go, and blah, 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 we go. I come here, we visit it again, right? Let's see if we pass anything. I passed something. So we hit a position, right? And then it's no good. Like, we can go. Like, we can keep going. Yeah, I mean, the problem is, let's just say we have all zeros, right? We have all zeros. And we go. And then in this position, we go, and then we will go back. And then in this position we will go back. It's in the path, right? It's in the path. So should we have a path? Okay, let's say we have a path, right? So as we go, we have a path is keep adding, keep adding, keep adding. And when we branch out, okay, let's try. But we cannot use LRU cache, that's for sure. So what we're gonna do is memo, right? Gonna be this for this in range. Let's say quota range k, range k. And I didn't even use k. Oh, I use k here. Right, so for this in range k, and each one is going to be starting with 0 times m for this in range n. Right, so that's our memo, and we have blah blah blah, and then path. Say path is a set, right? And what we're gonna use, okay, I know what you're gonna use. So anyway, if quota is larger than, we don't have to return, right? We don't have to return anything. If quota is larger than this, then we just say memo quota, right? And there's a path already added me, right? Path already added me. So a memo quota and ij equals this. Then we return. Otherwise, result is this, and then didj and blah 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 and blah 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 and blah blah blah. If there's end, right? Let's say ni nj not in path. If it's in the path, we visited already, and we don't want to visit again, right? That would be stupid to visit again. If it's not in path, and say if this is larger or equal to 0, then path, right, dot add nij, and then say res gonna be equal to min res, and no, we're just gonna do dfs ninj quota and path, right? This one will fill the memo. So -1, and then we say if this is larger or equal to 0, right? If this is larger or equal to 0, then I can start all -1. Right? If it's larger or equal to 0, then no, don't do it here. And also we have to say for q in range k, right? And memo q n-1, n-1, equal to 0. Right? This is fine, blah, 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 it's all fine. It's this, right? We can avoid adding if this, blah, blah, blah. I'm going to say if, and else, and then we have to remove it. So let's just add, path added, right? And then we're going to check if memo is it, then let me say if memo quota ning is smaller than 0, then we'll do DFS. So DFS will fill it, and then res equal to min res 1 plus this thing. 1 plus this thing. Okay, so that's that. And we can say we'll do one of these. Once we're done, we're going to say path.remove ning. So backtracking, right? Remove, and then go to the next one. So if quota is larger than 0, right? And then we're going to try. Same thing. Let's just do it. Let's just do it here. Add it and do a bunch of stuff, and then remove at the end. So if it's this, again, if it's this, then we're gonna do DFS and this. Right? DFS nj quota path quota minus 1, right? And then once it's done, let's eat 1 plus. Ooh. It's going to be quota minus 1, right? And once we're done, we do this, remove, and we'll do the next one, blah, 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 blah. And once we're all done, right, we're all done, we're going to do this, do my memo. This is going to be res, right? And we don't have return, that's just that. So we're going to do this, DFS 0, 0, k, and passing a set as our path, right? Once it's all done, we're going to return minus 1 if memo, right, k minus 1. Oh, which one? Rank k. Oof. Because we use quota directly, so it has to be k plus 1. Right? It has to be k plus 1. So now we can pass k, and then we can say with this quota, right, and I and a 0, 0. Let's try this. Ugh, just out of range. Out of range here. What? Well, Q in range K. Oh, shoot. That's N. That's M. So in range, actually K plus 1. Res is not defined. Oh, there's no res. This is this, or return this. Okay. Let's try. Right, if this one doesn't work, we are going to give up. Well, we do have another hint, so I don't know how you want to handle that. So run it, see. Oh, what the hell? My answer is 41, expected is 387. What the hell? This is like not even correct. How? Why would it not even be correct? I have a simpler, I don't know, man. Hey, this one's right. What I'm saying is that the logic is not right. -1, right? Then for every quota, the quota is 0, right? All the way to quota k. From 0 to quota k. And if I'm at m-1 and n-1, it's always going to be 0. And then say if the quota is larger or equal to number of obstacles in this position, right? Then memo quota ij, yeah. As we set resist this on the 4 directions, and we keep a path, and we say if this and this and n9 and j not in path, right? So I haven't visited it yet. We add this, and we say if grid is 0, this actually we can these two can be simplified in 1. Like if quota is large, if quota is 0, if quota is larger equal to 0. Now if it's 0, then we don't have to change the quota, we can just go, right? And then go to n9 and j. I will compute whatever n9 and j is, and then it's going to be 1 plus this. Otherwise, if quota, right, if quota is larger than 0, like the next one is not, the next one is a 1, right? It's a 1. If it's a 1, then I can still go, but I need to decrease my quota, right? So I need to decrease my quota. Okay. So next one, quota will be 0, right? And then we do it. Hold on. This seems to be math.inf. No, I don't think that's the reason. No, that's not the reason. This was right, right? I follow a path, and then I go all 4 directions, and within that path, I'm not going to revisit myself. And then, if the next one is 0, I can always go to it, right? That's fine. I can always go to it. And the quota is like that. My position is not good. Because actually in the next position it won't be good because my quota is depending on that. That doesn't matter. So say if the memo, yeah, I do think this is a sentinel. This is a sentinel. This is not anything special. It's just a sentinel to signify whether we have visited that one or not. So with that sentinel, smaller than 0, then we do this. The same quota, different path. And result, I'll come back, because I'm going to memo this, and then +1, because I take one step, go to the next one. Okay, I need this to be simpler. I need this to be simpler. Give me a simplified version, and we'll see how I can make it. Okay. Oh, no. Here is the trick. Right? Actually, I don't need to remove this one. Okay. So now what I can do is here and just delete. Okay. Yeah, let's make it this one. And the 4x, let's make it like 4x4. 1, 2. Nope. Okay. Let's see what's gonna happen. I hope this one I'm wrong as well, so I can like slim it down. Expected answer is -1. Okay, so it is a big issue. Let's see. It's about half. Oh, my bad. Move this. This one's correct. Okay, so let's try this one. Okay, this one's wrong. Good. Now let's remove from the front. Let's say I remove these. Yeah, it's correct. So let's remove the middle. It's also correct. Shoot. Maybe I just one at a time. Well, it doesn't take a while to remove all of them. Okay. Okay. I'm just removing the zeros. Hopefully I can get exposed. Okay. Nice. Nice. Keep going. You do it there. Let's remove 2. Nice. Yep. I think we can remove all of these, and then I will still give you a result. How about now we start removing the others? I don't know. I'm removing all at once. Ah. We don't want the zeros. Okay. Okay. Well, that's a very interesting test case, I think, eventually. We're removing everything with 0. Ah, we're removing everything with 0. Yeah. I see that. Which means I probably can do 1, 2, 3, 4. Okay. This is simple enough. Which means one. Okay. 2. Nope, it's still working. So maybe one more. Yeah, I don't remember how many I had earlier. All right, so that I think is a minimum I can conjure up. So it's gonna be 1, 2, 3, 1, 2, 4, 5 by 4. Okay, so 1, 2, 3, 4, 1, 2, 3. It's very simple. The first row is all zeros. Everybody else is 1, and the last row is all zeros. My result will give us 3, which is ridiculous. How could it be 3? Like, geez, how could it be 3? My God, this is ridiculous. 3 minus 1, right? How many of these 2? Yeah, they give me 3. My Lord. Row in non-obstacles print row. Let's see. Huh. That is not. Well, that is 3. Okay. So quota is 2, right? So yeah, that's 3, 3, 3, 3, 3. That's 2, 2, 2. Everything's 2. Everything's 1. Everything's 0. Exactly. Then I'm going through this. Yeah, this one is correct. So what? So as I'm going through this, just for row Oh my god. We have 3 levels. Q in range k plus 1, right? For row in memo Q, print row, and print separator. Okay, so this is 3. I don't understand. How is it? How? Hold on. If this, right, res equals this, and if nothing, res shall be inf, right? So inf. We'll initialize everything to -1. This will give us 3. I think I can simplify it even more. Let's do I think we can do like this, right? And 0. Ah, shoot. It's fine. Let's add another layer. Right? Nah, it is correct. How about this? Nah. It has to be 3. Okay, so what if I, do 3, but let's just reduce number of number of columns. So we get another 1, okay, and then we do this, 2, right? Yeah, and that is problematic. So we can do this, and should be -1. Just remove, right? And remove 1, remove 1, remove 1, remove 1. Okay, so when we start, we have 0, 0, quota is 2. So we don't have this. You know what? What if we remove 1 more? Ha! Dear God. I can remove 1. What if I remove 1 more? Right? What if I remove 1 more and it just become a column? And if it's a column, then I think we can do it as a row, right? All we need is 1, 1, 1. Nope. Maybe we're pushing it. We're pushing it. Let's try. Let's try. We gotta try. Gotta try. Yep, and no work. So this is the minimum. Right, so the other matrix is going to be, hold on, so 1, 2, 3, 4. This other matrix, that's going to be 0, right? And then this will be 0, this will be 1, this will be 1, this is a 1, so this will be 2, and this will be 3, and this will be 3, and this 2, 3, 3. So that's the number of obstacles. Now we're given, when we start, quota is 2, right? When we start, quota is 2. So what we can do is, let's not print this. Let's go like just step by step. So where we at? Right, so we're just going to say print ij and quota, right? It's at the beginning, we have ij and quota, and we're going to print this one as well. So we're going to print quota. You know what? That should be at the end, right? And the rest. All right. So ij. So we start. No, let's not start. 0, 1, 2. 0, 1. So we're at this position, right? At this position, our quota is 0. Right? The quota is 0. This is our thing. The quota is 0, and we cannot go anywhere else. So we're recording inf, which is true. So we have a quota, right? So quota q equals 0, and q equals 1, and q equals 2, right? Actually, yeah, I want to go through 4, 5, 5, 5, right? So this time quota is 0, and this one's inf. No, not this one. This one's inf. This one's infinity, which just makes sense. And then the next one is 0, 0, 0. Well, 0, 0, 0. Quota is 0. Huh? Quota is 0. How would quota become 0 at the start? Oh, it's going back. Okay. I mean, if quota is 0 and in this position, quota is 0 and anyway, so let's check this one. 1, 0, 1. Quota is 1, and I'm position 1, 0. How would it be 0. How is that possible? I'm at 1, so it's 0, 1. So I'm at this position, right? 1, 0. And my quota is 1. So I'm at this position, and I have quota 1, so I can go both sides. So on this side, what do I have? This one 1, 0. This one is 1, 1. So m is 5. n is 2. Right? So the 5 plus 2 minus 1 minus 1 minus 2. Right? So this time is 3 at this position. Yeah, it is 3. I don't understand. How could it be 0? You know what? This is not helpful. I don't want this. I want every single time I do this, right? And then I want to print ij. Let's put in parentheses. And then current quota. And then ninj. Right. And then memo. Right. This. And I'll do the same thing here. ij, quota, and nj, quota minus 1. Alright. Oh, we have minus 1. How does that happen? How does that happen? I'm at 1, 1. Okay. I'm at a 1, 1. I want to go to 2, 1. But I don't have 1 quota. So yeah, I can go to 2, 1. And then from 2, 1, I have 0 quota. And I have nowhere to go. So it will give me infinite. That is correct. Next I see is I'm at 1, 0. But here I'm at 1, 0. And I have 0 quota. And I want to go to 0, 0. How is that possible? It has to be not in path. How is 0, 0 not? Oh, shoot. I forgot to put 0, 0 in the path. Dang it. Okay, so now it's still wrong, but much less distance to travel. Okay, and now the problem. This is good. So 1, 1 at 1, 1, right? I want to go to 1, 0, and I can, but it will give me infinite. So this one will give me infinite. So I go from 0, 1. 0, 1 is here. 0, 1, I go to, oh, my network is not good. Come on. So 0, 1, I have 2 quota. That's true. I want to go to 1, 1, right? So yeah, I go to 1, 1, and 1, 1 gives me infinite. That's true. So that's it. So I go back to 0, 0. And I want to go to 1, 0, 1 and give me infinite. That is correct. So that's why 0, 0, 2 give me infinite. So okay, so now I'll go to 1, 0. Right? I go to 1, 0. Quota 1. That's true. And I want to go to 1, 1. Now I return a -1. What? What? 1 shall already register. One shall already register infinite. How is this returning -1? Right? I'm at 1, 0. I want to go to 1, 1. And this is -1. How? How? Right, so let's not print this. Let's not print this. Yeah, 1 is inf. You see that? 1 is inf. And 0, 1 is inf. 2, 0, 1, 0. 1, 0 is interesting. Okay, so we confirmed 1, 1 is inf. Right? 1, 1 is inf. So we're gonna say and 1, 0 is already inf. 2, 1 is inf. 1, 0 is inf. 2, 1 is inf. Right. 1, 0 is inf. 1, 1 is inf. 0, 1 is inf. 2, 0 is inf. 1, 0 is already inf. How does 1, 0 become 0? Hmm. You know what? I'm gonna, for this purpose, I am going to just do this and append pop. So at each position, I'm just going to print ij quota and path. You know what? Let's not do this. Let's do it here. No, it's not going to work. Let's try. Tuple cannot be interpreted as integer. Huh? What? quota on a path. What is this error? Tuple object cannot be interpreted as integer. I never interpret as integer. Oh, I see. Oh, I forgot. Yeah, you cannot. All right, so we're at 0, 0 with 2 quota, and then we go to 0, 1 with 2 quota, and I'll go to 1, 1, yeah, with 1 quota. Then we go to 2, 1, and then nowhere to go. So we backtrack to 1, 0. Now we go to 1, 0, right? And then nowhere to go. We hit 1, 0 again, but from 0, 0 to 1, 0, right? We go from 0, 0 to 1, 0 with quota as 1. That's why 1, 0 is visited twice. Yeah, 1, 0 is visited twice. Okay, so I see. So that's first to 1, 0, and that's the end, right? So also go here, 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 and then going back, and then I come here 1, 0, and then I go to 2, 0. Okay. So now with this information, let's not print this. I kind of know the path. So I know at the end, so we go to 2, 1, right? That's inf, right? So and the 1, 1, and I want to go to 2, 1, right? I have 1 quota, and then I want to go to 2, 1. And then 2, 1 returns to me an inf. No way. No. One plus math.inf is still inf. So 1, 1, right? And then 1, 1 trying to go to 1, 0. And then that returns inf as well. Oh, that's because it's different quota. Okay, that's fine, right? And then, so 1, 1 is no-go. So 1, 1 itself is no-go. And 1, 1 itself becomes inf. So now we go back up to 0, 1, right? And then 0, 1 with 2 quota, trying to go to 1, 1. And 1, 1 with 1 quota says, and no way, nowhere I can go. So 0, 1 with 2 quota is going to be inf, right? Now we're back to 0, 0. We want to go to 0, so 0, 0 with 2 is going to be inf. Now 0, 0 is going to be 0, 0 go to 1, 0, right? So it's going to go to 1, 0. So I go to 1, 0. At 1, 0, I have quota as 1, right? 1, 0. I have quota as 1. And then I want to go to 1, 1, right? I want to go to 1, 1. So in 1's case, and 1 is not a, so it's down here, right? Down here. So I say memo quota -1. Yes, quota -1. Okay? So in this case, I think these will all pass. So I have to comment on this. And let's get back to the set. Set saves time. And then this is going to be add. This is going to be remove ing. Okay. All right. So the only thing changed is quota -1. All right. The only thing changes here. So I'm going to put this one inside. Run it. Oh, all right. Do we dare? Let's try it. Pending. Oh, yes. Oh, yes. Oh. All the satisfaction. All the satisfaction. Oh, wow. So we are correct. We are correct. The only thing is just, I don't know, man. I got, oh. So we spent like what? I'll say about an hour. Probably not that long. Maybe 45 minutes. Trying to figure out this stupid bug. It's a really stupid bug. Yeah, we know that something is wrong. But just, you know. I should have realized, because we know we did check quota -1. And I just forget to put quota -1 here. Damn. Damn, man. This is ridiculous. Okay, we solved it. All right, let's see the runtime. Oh man, what an effort! What an effort! Not bad. The runtime is not bad. So, all right, what do you want to say? I don't know, man. I'm completely speechless right now. I don't count this as using a hint, right? Because the only thing the hint tells us is use BFS, and that's it. That's the end of the story. So I'm not going to do that. But what I am going to do is just write out what our idea is. So first of all, this is a hard one. This is a hard one. Hard question. And I got stuck on a stupid mistake. If I had not committed that mistake, I would have finished. I would have finished 45 minutes earlier. Anyway, so let's just say, first of all, I compute a matrix that records the number of obstacles, right? The number of obstacles, the minimum, right? The min number of obstacles each cell must encounter if we reach the destination in minimum number of steps. Now it is deterministic that the minimum number of steps from ij, right, from ij 2 m minus 1 n minus 1 is m plus n minus I minus j minus 2, and the path must be a zigzag, right? Must be a zigzag going right or down. So we can compute this num obstacles matrix by going from bottom right, from bottom right to top left. We can do that, and at each ij, the minimum number of obstacles is the minimum value of num obstacles I plus 1 j, right, num obstacles I and j plus 1 if ij is an obstacle, otherwise, or 0 otherwise. The purpose of this num obstacles is that when we reach a cell with the current quota, right, current quota larger or equal to num obstacles ij, that means we can reach the destination with the minimum number of steps. Next, we perform a regular DFS, right? It's just a regular DFS. The only thing is, a regular DFS on the original grid. The only trick is that if the next step is an obstacle, we can choose to still visit that cell, but we must reduce our quota by 1. Therefore, to memorize this, DFS, we need 3 levels: I, j, and quota. So, at each cell, ij, right, we look over all its neighbors, all its valid neighbors, that is within the bound and not being visited, right? Valid neighbors. If the neighbor, right, if the valid neighbor is 0, right, we visit it without decreasing quota. Otherwise, we visited with quota decreased, except when quota is already 0. Then we cannot visit a cell that is an obstacle. Right, and that's basically it. The answer is memo k 0, and 0. So we run OMN here, and for this one, because we memorize, so each one is the ones. So I think the total is going to be O, M, N, and K, right? Where M is number of rows, and number of columns, and K equals to K. And this one we go 128 milliseconds. How many people do you have in your group right now? How many people do they have? Oh. Where's the deadline? How much work do you want to do? Are you confident that you can finish this with minimal help? I will not join. You join, you don't have the say. Right? All right, let's take a look. Wow, what an effort. It's pretty brutal. I mean, actually it's not. I think the logic is pretty straightforward, and we got stuck of this stupid bug. I mean, in an alternative universe, I will not make this. I'll not make that mistake, and then we'll all be good. 1293. So 1293. Oh, I think I pressed the wrong button. Dynamic programming. Study plan. No, I don't want study plan. I want to see the result. Good question. Discussion. I submitted what? 2 times. Alright, short BFS. Nice. Let's see how short. Ah, my dear God. Beautiful. Beautiful. Complexity. So we have the same complexity with state. Coordinates and case, the number of obstacles we still can remove. Oh, that's true. Oh, wait. How do you... And use a Q. Oh, it is a BFS. Big enough. Line K larger or equal to. Okay, let's see. M plus N minus 2. Yeah, if K is larger than M plus N minus 2. Ah, that's true. That's true. Okay, so if this return this, and we have a deck 0, 0, 0, k, and a set steps, number of steps, x, y, and k. If this returns steps, otherwise for 4 directions, if within and k minus grid larger equal to 0, so we still have enough quota, then new equals dx dy in this. If new not in v, v dot add, and q dot append steps plus 1 plus new. That's it. That's it. So BFS, right? BFS. Why do we use BFS? Because in BFS, when we reach the destination, the first time when we reach the destination, that's the minimum steps, right? That's why we do BFS. Now, but as we do in BFS, I think the ideal is we should not think about the grid anymore. It's just, BFS is just a concept, right? The concept, the next level, the next level, the next level. And on one of the level, so yes, so basically what happens is we can go to the next level. We can always go to the next level. And we can go to that level only if the quota is allowed. If the quota is not allowed, then we cannot visit that cell. If the quota is allowed, then we can visit it, and then we can always push that in. And we just keep, oh wow, that's so simple. Wow, it's so simple. It's so simple. This should be a medium question, right? I think the only trick is just need to add use BFS. Use BFS. Basically, it's just one more check. That's it, right? That's it. That's all the trick it is with this problem. It's just one more check. We have to go around. We did go around. All right, let's code it up. This is good. This is a good trick, and it's worth it to code it up. Yeah, I mean, like, you just need to have a path, right? Make sure that you do not go. Yeah, we just have a path. It's not a path, it's visited, right? The cell that has been visited. And when you do the cell has been visited, it's the position and the quota, right? It's just that. So what do we have? Well, we're gonna have same thing, mn, right? And if m plus n minus 2 is, if k is quota larger or equal to this, then return m plus n minus 2, right? So quota is larger than minimum steps. So definitely, so we can always take min steps. That's what this one means. It's a nice trick. Oh, I have to also credit the guy. This is from the Bob Beacheff. is cred. Right, so this is from here. It is very simple. Using BFS, the benefit, right? The benefit, or using BFS is that the moment we hit the destination, we have accumulated the shortest distance, right? The only trick is when we add, well, there are two tricks. There are two tricks. First, when we add a new cell to the path, we need to, right? We need to check the quota as well. So it's to check quota as well. Second, when we cache the cells already visited, we need to also include quota. Basically, each cell can be represented, right, by 3 dimensions. 3 dimensions, I, J, and Q. That's all. That's all there it is. So when they say Q and visited equals to this, and what's visited, it's set, right? But when I say steps I, J, and K, right? The same thing, steps I, J, and K. That's initial state. Steps I, J, and quota. While Q, right? Then we just say steps I, J, Q. I say quota equals temp is this for this in Q, right? So this in Q, we're going to see its child. So we say for Ni and J, right, in I plus 1j, I minus 1j, j plus 1, and I j minus 1. So if zero small equal to ni smaller than m, and 0 smaller equal to nj smaller to n, and it's one visited, so the quota I have must be larger or equal to grid ni nj, right? If this is 0, I can always visit. If it's 1, I can only visit if my quota is 1. If quota is 0, I cannot do it. So if it's this, then we can always add it to the queue. So temp dot append, right? Append what? Append steps plus 1, ni and j, k and quota minus 1. and visited. Oh, I have to check visitors first. So next new equals this is a new one, right? This is the new one, and if new not in visited, then temp gonna do this plus new and visited.add new. All right. Once we're done, q equals temp. Yeah, quota. And then if I equals n minus 1 and j equals n minus 1, return steps. And then if BFS is done, return minus 1. The hell? Huh. Did I do something wrong? For directions within, and then quota is larger or equal to grid nj. Yeah. And then new, right? And when we go to new, then the quota in new must be minus 1 nj, right? And then temp.append steps plus 1, yeah, and plus new. Oh, hold on, this is wrong. Visited, this is 00k. But no, that's not the problem. Oh, why quota minus 1? Quota minus this. Why quota minus 1? There we go. So that is the solution. BFS. BFS. Oh wow, very fast. Or twice as fast. Same thing, M and K, 72 milliseconds. Very fast. Alrighty, I mean, we are not slow because we have this, right? We have this. Basically, the case that this one can solve, we have to go through this one first, and after we go through this one, and then we'll hit this. That's why it's 128. But still, good solution. Very, very good. All right. Like I said, yesterday was very easy, and today was, yeah. Actually, I don't think this one is this one's like a hard, like an easy hard, and a hard medium. I should have finished it earlier. Yeah, should have been like a 1 hour. It's a 1 hour problem. All right, I'll see you guys tomorrow. Adios.